Swayam Prabha. Digital India. Educated India.
In this module, we will be talking about acoustic quality indicators. There are two modules in which we will be looking at acoustic quality indicators. This module primarily covers the criteria for background noise, what all are the indicators or indices which we have to understand before we set the background noise level right in a given space. And next we will be talking about criteria for acoustic quality, that is good listening, how it starts. So the second part of this will cover further more indices. To start with the background noise levels, how do you define background noise level? One of the last modules we looked at the environmental noise levels, where we talked about L equivalent and how these limits are defined. So in case of indoor noise levels, we define in terms of one of the basic indicator is noise criteria, commonly referred as NC. Many of the standards define saying NC 30, NC 40, NC 45. A common indicator that you would find in most of the standards internationally, you will find this name NC 30, 40. These things will be given, and depending upon the type of space, what activity happens there and what is the acoustic quality which is required, this noise criteria varies. Noise criteria or NC, this is a single number index which is intended to define the design goals, how much should be the allowable background noise level in a given space. Instead of saying the overall noise level, sound pressure level or sound pressure level L equivalent should be this much, this is a better indicator. This derives from these curves. I will explain this first. On x axis you will have the octave band center frequency, this we looked at. Here this covers from 63 Hz all the way up to 8000 Hz. Further low and further high frequencies are not covered here. Primary audible frequencies, it starts from 63 goes to 8000 Hz. On the y axis you will find sound pressure level in decibels. There are defined contours which have been evolved. So if you take for example noise criteria, a particular noise criteria of say NC 20, then you will find in the center frequency, that is 1000 Hz, you will find close to 20 decibels or slightly more or less in this band. As it goes up, it reduces, and then as it comes down to the lower frequency, this value goes up. This is more or less similar to the audibility capacity of hearing that human ear has. In the lower frequency, more sound pressure levels are allowed. Say for example, if a standard defines that you have to meet NC 40, noise criteria of 40 in a given space, take it as an office space, open plan office space, a noise criteria of 40, NC 40 has to be met. In what it means, how it translates, at 63 Hz you can go all the way up to 65 decibels at 63 or very low frequency. Say in mid frequency somewhere around 500,000 or 2000 Hz, you have to be close to NC 40, that is 40 decibels, and then at high frequencies it should be relatively low. Say 8000 Hz, NC 40 would actually mean you will have to meet somewhere around 37 or 38 decibels. So if you have a spectrum analyzer or a sound pressure level measuring device, you will have to meet, or after you design, the room has to meet at 63 Hz. It should, it can go as high, it means it can go as high as 63 or 65 decibels, but at higher frequencies like 8000 Hz, it should be well below 40 decibels. That is what it means. Then if you are trying to meet this, then it means you have met the noise criteria which is defined. There is a lower line which is threshold of hearing, and noise criteria which is close to 30 or below, which means it is a very quiet ambience. This is moderately noisy to noisy, this is between 30 to somewhere around 50, above 50 close to 60, 65, this is very noisy, and above 65 this would be termed extremely noisy. So depending on the space, for example, there is a difference between a commercial area where the NC is defined versus a quiet open office versus a private office and a boardroom, the NC or the noise criteria would considerably differ. As we know, sound pressure level is also easy to express in terms of A weighted. This also A weighted also means that you are weighing it to the human ear's capability of hearing. These two can be compared or they are comparable. For example, take a noise contour or NC criteria contour of 40. This would be more or less equal to an equivalent sound pressure, A weighted sound pressure level of 50. So there is a relation. They are also directly proportional. As this increases, this also increases, but still there is a considerable amount of difference. This is termed, or this was found to be more precise in representing the background noise levels in rooms. I am going to give you a specific example. This is an open plan office, a plan, a top view of an open plan office. We took measurement in few specific locations. In about 6 locations we measured the acoustical quality. I am going to give you, take this as an example further wherever we come through acoustic quality indicators in terms of offices. I am going to cite this example. Remember this image, this is a very symmetric looking open office. 6 positions we were measuring, like inside the workstation. These are cubicles, say each of these makes 4 workplaces all across. We took along the aisles plus within close to the workspaces and few specific locations. So in a typical open office, if you take the core area, you will have, for example, there are 2 times we took the measurement. What you see in the background is a noise criteria, the same curve that I showed you, and these dark lines, these represent our measured value. There are 2 things here. This represents the non-office hours, the one here. Before the office started or after the office is people have left, 2 main things happen: air conditioning system plus the computers, photostat and reprographing machines and other typical machineries are turned off, plus people talking and conversational background noises are also coming down. Due to this, you find the background noise level to be low. If you estimate the noise criteria, we got around 38 NC. So if the office standard for open office says you have to meet 40 noise criteria, when people and machinery are all machinery is turned off, people are not there, then we are getting somewhere close to 38 as the noise criteria. But then when you are measuring during office hours, we find low frequency, there is little high, probably due to machinery and reprographic background noise levels. Then you also have people conversing, which also increases it. We found we got around 53 noise criteria during office hours. So in our example, say if we have to meet 40 noise criteria, we will not be actually meeting it. We will have to go for certain kind of acoustical treatment in order to bring the noise criteria to a lower level. This is a one of the private offices. This is the same open office, but in the periphery we had a couple of cubicles where private cabins, office cabins for senior people. We did a measurement there, but if you take private offices, we found during non-office hours versus office hours, they were more or less closer, because just it was one person occupying with minimum amount of machinery sound. It was the air conditioning sound plus just a laptop and a person sitting there. So more or less with these measurements were taken for about 1 hour duration, continuously they were recorded and these were estimated. So we found more or less they were closer, 40 with office hours 45. But one thing we have to note, the definitions for noise criteria will vary from an open office to a private office space. Here the noise criteria requirement itself would be lower. It may not be as high as 40 or 45. They may ask you to meet a particular standard, might ask you to meet a noise criteria of say 35 during the office hours. Then again we might have to go for a treatment. This is one indicator of how the background noise levels are existing. Specific standards, there are different versions, standards defining commonly accepted form of version. Conference rooms are rooms for lectures 30 to 35, small open offices 35 to 40. This would also include private cabins. Then large offices you can go as high as 45, shops, garages it would be higher, and industries it can go as high as 70 NC. This is in terms of noise criteria. There is another version of defining background noise level. If you closely look at the previous graph, you had frequencies ranging from 63 Hz all the way to 8000 hertz. Typically if you want to understand what an air conditioning system causes and what is its impact on the noise level. Air conditioning system, HVAC system, comprises of fans, pumps, motors, air handling unit, the mixing turbulent sound, plus the passage of air also causes turbulence, the throw of it. Together there is an impact or an elevation or escalation in the indoor noise level. So if you have to understand them closely, you have to go beyond what frequencies are presented here. That is exactly what was done in this. This is called room criteria, or commonly referred as RC. There has been many versions. The current are more commonly referred as RC Mark II. There has been many improvements in this room criteria thing. These are certain definitions or criteria which are set by standard. So the current one is RC Mark II. This is a similar graph. You have the octave frequencies, octave band center frequencies in the x axis. Difference is it goes up to the maximum, it goes up to 4000 hertz, but minimum earlier it was up to 63 hertz, now it is further going to up to 16 hertz. So you are actually considering or starting to consider much lower frequencies than what noise criteria actually allowed for. It was primarily developed to consider the low frequency and mid frequency associated problems in terms of primarily relating in terms of HVAC noise emissions. So if you look at a air conditioning standard like ASHRAE, they would ask you to adhere to certain room criteria, because you are designing the HVAC system as a mechanical engineer, as a HVAC engineer. Finally you will have to meet the room acoustic criteria or the room criteria. There are 3-4 specific things which we have to note. I mean, as the earlier thing, there were curves there saying noise criteria NC20, NC30. Here we have room criteria starting from 25, it goes up to 50. There is a threshold of hearing. One thing interesting, if the frequency levels go below, say for example 63 hertz or say 16 hertz, there are not much of the frequencies which our ear can actually sense and appreciate. At this frequency, when sound is emitted, this will be felt as vibrations, direct physical vibrations rather than audible sounds. Very high sound pressure level or decibel levels only can be heard at, for example, 16 hertz, but before we start hearing it, you start feeling the physical vibration. There are two zones defined here, zone B and zone A. These are, if you take zone B, these are regions where there is a probable vibration and these are specific vibrations. Say for example at 16 hertz, your spectrum analyzer shows that you have a sound pressure level of say 65 dB. It means there is a probability for vibration, or at least the ducts or machinery, HVAC system going to cause a probable vibration. At zone A, the levels are even high. This would indicate that there is definitely certain vibration which are going to result. Apart from this, there are 3 lines, line D, line C and line E. We will look at what they mean. Neutral, for example, a neutral level or RC neutral means each of these octave bands, the sound pressure levels are lying below these dotted lines here. There are 2 important criteria, one is rumble, other is hiss. Rumble is a low frequency indicator and hiss is a high frequency indicator. If your sound pressure level, say you are keeping a spectrum analyzer again, you are measuring it, if your low frequency sound pressure levels are exceeding this particular line D, this dotted line D, it will indicate you are going to have a rumbling sound. They are actually trying to categorize the sound itself, the character of the sound itself. You will experience a rumbling sound, whereas if your sound pressure level spectrum analyzer measurements are going to cross line E at these frequencies, at slightly higher frequencies, then you will be experiencing a hissing sound. This is what actually it means. Then as I said, if they cross and get into the boundary B, then you will be, you can expect probable vibrations, and when they go into zone A, it means there are going to be certainly some vibrations associated. Main things where vibration occur is the HVAC ducts, where the turbulent airflow causes certain vibrations. A typical example of the same office which I was talking about, when we measured, there was no rumbling sound, but there is a slightly hissy sound because it was trying to touch, not really cross, but it was trying to touch the E line, but pretty much the room criteria was met. Only problem was the noise criteria was slightly above. There is a striking difference here. If you find the room criteria to be acceptable, you can infer that you do not have to really rework on the HVAC system or the design or treating the HVAC system itself. You might probably then take, make sure or ensure that this HVAC system does not have much of the impact on the noise level. When noise criteria is not met, your main attention should be on the room acoustic treatment. Whereas if you see the room criteria is shooting up, it means your main attention you have to focus on the air conditioning system. There may be certain problems, I am saying you have to prioritize looking at the air conditioning system associated noise levels. So we looked at two indicators for background noise levels. We will look at one of the important indicators for the indoor acoustic quality. It is a very common term, it is a day to day, this term is in day to day use, reverberation time. This is one of the first indicator, this is not the only indicator of acoustic quality. Among several indicators, this is the most commonly used and one of the simple indices which you have to understand. Reverberation time, it is a time required for the reflections of a direct sound to decay by 60 decibels. Let us look at it in this way. In x axis, I am going to have the time, we will talk about milliseconds, because the velocity of sound 340 meter per second, 343 meter per second more specifically in room temperature indoor. Then the time within which the acoustic wave would reach you even in a very huge auditorium would be in milliseconds. You will not even experience few seconds, it will be very few milliseconds the sound would reach you. Let us take this as sound pressure level in terms of decibels. So let us say there is a, say this is 30, 40, 50, I am going up to say 100 decibels now, say 110. Now there is a background noise level, like we looked at, say it is a a small lecture hall, you have certain background noise level across the time. You are going to create a impulsive sound, say for example you are bursting a cracker. What would happen? There would be a sharp sound which goes as high for example as 110 dB, then it would not decay that fast, but it would eventually be decaying, there will be a slope and then it would come back, after a while it would come back to the background noise level. Imagine if the background noise level is around 30 or 35 decibels, then you are elevating the sound pressure level and it takes a while to reach the background noise level again. Now here it is again continuing with the background noise level. If you mark this peak point as 0 milliseconds, that is 0 seconds, this is the start of the thing, and this for example takes about a few milliseconds. Let us talk about seconds first, we will come back to milliseconds later. Say now if you are considering this in milliseconds, say imagine it is taking about 1 second to come back to this point. The slope of this line is estimated and the time taken between this and this, that is the reflections of the direct sound. So this is a direct sound at this point, this is a peak direct sound, it can be a clap, it can be a gunshot, or it could be a cracker or any standard sound source. You are elevating the background noise level and then you are letting it fall. The cracker is just one impulse, it is falling off, it takes about 1 second. This is exactly what you call in terms of reverberation time. It is expressed in seconds, reverberation time is expressed in seconds. The simple formula is used here. Reverberation time is a factor of the room volume, V is a room volume. In the denominator you have a factor called A, V by A, and you have 0.161 or 163 marginal variation, TR is a reverberation time, and A is a acoustic absorption. It is expressed in Sabin's. Sabin is a person, name of the person who did all these physical experiments, and finally he derived a relation between these parameters. A actually is a factor of S, that is the surface area, and alpha, which is the absorption coefficient. We will look at more about absorption coefficients in one of the following sections. Alpha is absorption coefficient of a material, and S is a surface area of that particular material. Say you have a room of, for example, 4 meter by 4 meter and the height is 3 meter. It is a very small room. You have wall surface plus you have a floor carpet and you have a false ceiling. So without forgetting any door, window, anything, it is a sealed room. So with a simple room you have 3 different materials. First is the wall surfaces, the surface area of the wall. If you have to compute reverberation time, the first thing you need to do is compute the surface area of wall surfaces. So you have 4 walls, it is a 4 by 4, 4 meter by 4 meter room, 4 by 3 meter, you have 4 walls, this will be the surface area. The wall, it does not have any absorbing material surfaces. The absorption coefficient ranges from 0 to 1. 0 means it is perfectly absorbing, 1 is totally reflecting, it is a coefficient. Say for a typical reflecting without untreated wall, the reflections probably will be around say 0.85 or 0.9. There is no absorption happening within the wall surface itself. So let us take it as 0.9. Then what you will have? You will have to multiply the whole thing by 0.9. So this is alpha 1 S1. This is the first surface we are considering. The next surface would be say the floor surface, that would be say alpha 2 S2 will be 4 meter by 4 meter, this is a floor area, into, I said it is a carpeted floor, let us say the absorption coefficient. I will define more about and talk more about the absorption coefficient. It varies with frequency spectrum, it is not a single number for all the spectrum, it varies according to frequency, but let us take one number right now. Let us take the carpet has an absorption coefficient of around 0.5, that is 50% absorbing. Then you multiply this by 0.5. The third surface we talked about alpha 3 S3, that would be the ceiling, again it is 4 meter by 4 meter. Let us take alpha 3, this was alpha 1, alpha 3 to be for instance 0.6. You have a false ceiling, not a very strongly absorbing false ceiling, a simple gypsum false ceiling, then you will have 0.6 here. If you take sigma, you sum it up, you get a number called A, defined in terms of, or the unit of measurement is Sabins. This goes to the denominator, you have the room volume in the numerator, you multiply the whole thing, you will get directly the reverberation time. Very simple formula here. A logical understanding goes like this. If you have to improve the reverberation time, say you have to typically longer reverberation times are longer time for decay of the sound. Instead of 1 second, if this were to decay all the way here, instead of this is going to take say 3 seconds total from this point to this point. If it is taking 3 seconds, then the reflections stay in that room. Imagine you are entering into your new house, you do not have any furnishing, you do not have people staying, nothing is there, just an empty room. If you clap or if you try and sing, if you talk, you will be hearing lot of reflections. There will be a ambient sound which is continuing, which is not decaying out with closed window. But then eventually you start occupying, you put in your furnitures, you have your open windows, people around, everything is absorbing or scattering the sound, then the reverberation eventually comes down. This is exactly what we are talking about. If it is 3 seconds, there is going to be a lot of reflected sound. As I earlier said, the time taken for sound from the source to reach the receiver, the point receiver, will be in terms of milliseconds. Initially if you remember we were talking about milliseconds here, we will come back to that discussion, but this will be in milliseconds. But if you have reverberation time very long, say for example 3 seconds, 4 seconds, then by the time the first, say this is a first clap, say you imagine you are clapping or spelling one word by the other word, the first word reaches the person's ear in a few milliseconds, then you will have the second word spelt, the second word will be coming, but by the time if the first signal has not decayed down or the reverberation time is high, then this would start masking the second one. Imagine in a hall you are sitting here, a person is talking here, talking from this place, you are seated in this area, you also have the reflections from floor, ceiling, more clear picture of it. So you are sitting in a space, there is a podium, you are seated here, there is a direct sound coming here, say imagine you have a few milliseconds, x milliseconds, then there will be a reflected component, there will be many reflections, each surface will reflect and there will be sound reaching you. If these sounds does not get absorbed or decayed down within, say for example 0.8 or 1 second, 0.8 second or 1 second, then they will start interfering with the second signal. So this is signal 1, when the signal 2 starts coming in, they follow each other in milliseconds, like when I am talking I am spelling each word within a few millisecond gap, there is no much of time delay. So they will start masking each other, we will be looking at it more in detail, but this is so critical. If you start introducing an absorptive layer here, if you start introducing absorptive layers all around, then these sounds, the longer reflections are eventually getting absorbed. Moment they are getting absorbed, then the masking effect eventually comes down. This is exactly what we are trying to do. So in this context, if you are wanting to reduce the reverberation time, that is where we are talking about, say imagine the original reverberation time was 3 seconds, you want to bring it down to 1 second. There are different methods to do it. Common method which industry any kind of material seller would tell you is to go for an increased absorption coefficient. Instead of using a 0.5 absorption coefficient, we had our alpha 2 as 0.5, alpha 3 as 0.6. Instead of 0.5 he would advise you to go for 0.2, or instead of 0.6 he will say go for 0.2 or 0.3, and he will say treat your wall surfaces. So instead of 0.9 this can be made easily to 0.4. With all these conditions you are increasing the number in the denominator, that is the total sabins will go up. With this the reverberation time can be brought down. This is one method, but there are other methods. You can vary the surface area, instead of treating the whole wall, whole ceiling, whole floor area, you can pick and choose, you can increase or decrease the surface area which you are treating. There is a third method, you can look around the volume. If you think 3 meter or 3.5 meters height is not required in your case, then you can reduce it to, say imagine you are reducing a 3.5 meter room to a 3 meter, you are actually reducing the volume here. If the volume reduces, reverberation time will go down. If you take large auditoriums, cathedrals, opera houses, they are huge in volume, the reverberation time will go as high as 2.5 seconds, whereas small lecture halls, small rooms, you will the best designed hall would have a reverberation time of somewhere about, say a classroom would have a reverberation time expected around 0.8 to 1 second. Less than 0.8 you will have a better audibility. We will look at audibility more in detail, but simply speaking this is a relation between the volume, surface area of absorption and the absorption of the material. Three things you can determine the reverberation time. It also is a factor of frequency, as I said, it varies with respect to the frequency and also it varies with respect to the relative humidity, but in common calculations we do not get too much into detail, but this is, yes, in fact this is accountable, you cannot simply ignore it, but still for a simpler understanding in this module you can go with around 0.163 or 0.161 V by A is in Sabin's acoustic absorption, which is a factor of the absorption coefficient and the respective surface area. There is a term called T60, which is 60 decibel. The sound has to decay by 60 decibel. In this case, you have a sound pressure level of 110 dB. This is a maximum. From 110 dB, the sound pressure level has to decay down by 60 decibel. It should come down. The total decay should be 60 dB. This is here increased. It has to drop by 60 dB. The time taken for drop by 60 dB is actually what you measure as reverberation time. A simple reworking of the formula, you can actually find out what is the expected absorption. So if you have the required absorption and the actual absorption, you can find the expected reverberation time and the actual reverberation time. You can find what is the expected absorption. This is a typical field problem. You already have a room in which you have to add absorption material. How much amount of absorbing materials you will add? Substitute it. There is a existing absorption alpha naught. You have the reverberation time existing and the reverberation time which you intend to achieve. Say you have a reverberation time of 2 seconds or 3 seconds, you would like to bring it to 1 second. Substitute it, your current alpha, that is the existing absorption, you will be able to find what is the expected sound absorbing coefficient which is required. There are different methods of determining reverberation time. We looked at the Sabin's formula. Apart from this, there are 4 other commonly used things. They again vary based on applications. Eyring's method, Norris method, Millington-Setti, Fitzroy's equation. These things are also applied for detailed acoustic calculations, specific Hall types, specific absorption types. Sabin's model cannot be extrapolated, so you will need a detailed working. They also have certain principles like image reflection method, certain things are assumed here. I am not going to get into details of these models right now, we will stick to the Sabin's method. A typical sound spectrum analyzer, there are different classes. Class 3 very simple, you will only get a sound pressure level SPL, you will not get the frequency spectrum. Class 2 you might get frequency spectrum, some of the manufacturers do it. Class 1 is for long term recording, you can also have statistical parameters reflected with it. You also get, apart from the basic A weighted, C weighted or linear levels, you will also get a signal recording function where you can record for say specific duration 8 hours, 12 hours or for even longer duration, it will be recording, that capability is there. Then it will also record in terms of different frequencies, it can record single octave, third octave. As the class goes up, the complexity of the spectrum analyzer increases. Basic sound level meter of class 3 to a detailed spectrum analyzer of class 1. Let us talk about a practical problem now. We talked about a quiet ambience. You are trying to measure background noise level of an auditorium. Here we talked about a background noise of 30 or 35 decibel. In an auditorium, a background noise level with air conditioning system typically will range somewhere between 40 and 45 decibel. There will be certain disturbances, you cannot have a very quiet. If the auditorium is getting larger, you have an air conditioning system running, it is hardly possible to get something below 45 decibel. So your actual background noise level is here. Then when you say the peak level, there will also be certain masking here. So it is a good idea or a good practice to leave a 5 decibel threshold here and another 5 decibel threshold here. So now already we are in 50 decibel, the maximum we have come down to say 100 or 103 decibels here, leaving certain undulations on the top, because you cannot perfectly reach 110, it may slightly vary. So assume you are in 100 decibel minimum possible. Again this was a background, in our case the auditorium case this is a background, and after the decay it is going to come down to this point. This is the peak level which we are assuming. How much is the decibel left? 50 decibels we have, but if you have to determine RT 60, that is 60 dB decay, we are not able to get a 60 dB drop here, which means the sound source which we are using should actually go to 120 dB or 115 dB, so that you get enough cushion for a physical field measurement. In practical measurements this is highly difficult, like measuring directly RT 60, either you will need a very quiet ambience or a very high decibel, impulsive source with which this would be possible. So, for a common use, a better indicator is, instead of reverberation time 60, it is reverberation time 30, that is the decay of sound by 30 decibels is taken. Most of the sound level meters, or almost all the spectrum analyzer sound level meters, will have RT30 as a function. You will not find reverberation time 60. One more thing you have to note, RT30 does not mean it is half of RT60, it is a interpolated value where the slope is primarily considered. It is not that this would be RT60, then you take half of it, it is RT30 is going to be just half of RT60, it is not like that. It is an interpolated value, you are actually counting the slope or the decay, this particular slope is taken. As I said, you have level 1, that is a peak level, you leave a cushion 5 decibel, you count 30 dB decay, then another cushion, plus you keep a noise margin here. The background noise level, for instance, if it varies, fluctuates between this, you have T1, it starts actually from T2 because you are leaving a cushion for specific undulations. It also has certain functions in terms of acoustic defects, we will talk about it. You have T3, this is your threshold, then you leave the noise margin. This is a better prediction rather than counting a very huge slope and then calculating it. So, RT30 is most commonly used indicator, measurable directly in the field apart from laboratory conditions where RT60 is quite possible. It is not that it is not possible, but RT30 is more practical for field application. You also have RT20 for a short measurement. You have something called EDT or early decay time, which is also important to count lateral reflections. Lateral reflections are something which come to you like from the side walls, from the initial ceiling reflectors or the floor planes. We will look at EDT and the reflections in a short while, but you should know that there are different types of reverberation time. RT60, that is decay of sound pressure level by 60 dB, RT30 which is 30 dB decay, T20 which is 20 dB decay, and early decay time corresponds to a 15 decibel decay or lower. It is a early reflection corresponding to early reflection and its decay. Most commonly used, as I said, is RT30. These are certain common reverberation times which are specified. If you look at one end, a recording or a broadcasting studio, a small recording studio, the theatre kind of recording theatre, most commonly found in radio stations and your broadcasting, typically TV or radio broadcasting stations. They are highly absorptive, typically small rooms where a reverberation time as low as 0.4, 0.3 is expected. Typically classrooms, you can expect, as I said, somewhere between 0.5, 0.6, it can go to 0.8, 0.9, sometimes you will find 1 second, it is not bad, somewhere around 0.8 is advisable. As you go, for example, lecture and conference room, instead of small classrooms you go to lecture rooms or conference room, slightly larger one, then you can go up to 1.2, 1.3 seconds. As it goes to cathedrals, you will find as high as 2.6. Similarly, for symphony and kind of orchestras, it depends on what kind of play is performed. If you look at it, symphony for classical to romantic, then the reverberation time is different. Orchestra, chorus and organ, when organ pipes are used, you will need really high reverberation time. You also see in cathedrals, you also have organ pipes, choirs performed, you will essentially need a higher reverberation time to appreciate the music better. Dance and rock bands, again lower RT is sufficient. If you look at this side, these particular things are for speech. For speech performance, you will require slightly lower reverberation time, somewhere 1.2, 1.3 or lesser, not more than that. Both speech and music, if you are designing multipurpose hall, it may vary somewhere from, as such you cannot get very small because the auditorium, if you take, the volume is very high, naturally the reverberation time will be higher. Then you will expect somewhere between 1.4, 1.5, it can go further higher also. It depends on what type of speech and music performance or instruments are used. Then specifically for music theatres, orchestras, opera houses, you will essentially find reverberation times somewhere ranging from 0.8 or 1 second all the way to 2.5, 3 seconds. Another thing is spaces with low reverberation time like say 0.2, 0.4, 0.5 seconds are termed as dead spaces where the sound decays very rapidly. whereas those with higher reverberation time are called live spaces. One important thing you have to notice before you practice in the field, you should be aware that not always lower reverberation times are good. You term it as very dry space or very dry sound. You always need certain amount of reverberation time. 0 is not possible unless it is a very controlled space. Somewhere around 0.8 to 1 second is appreciable even for speech performance, whereas when you have instrumentation playing, depends, say if it is a violin or a stringed instrument versus a percussion instrument, depending on the type, or a wind instrument, depending on the instrument type and the sound it produces, the frequency spectrum it produces sound, you will require a different type of reverberation time. So do not try to make the space too much absorptive. Don't put too much of insulation material, don't put too much of absorption material specifically, so that the room becomes too dead. You have to have a live room to appreciate speech, music, whatever. The syllables have to have a continuity when you especially have music performances. Even for speech, in order to reinforce the original sound, the signal versus the reinforced reflected sound, initial reflections we call, or early reflection, you need certain amount of reverberation in order to avoid difficulty in speaking for the speaker and an appreciation of listening for the listener's side. So certain amount of reverberation time is needed, not too high, not too low. It depends on various factors. It depends on the speech intelligibility, primarily is affected by reverberation time. The speech becomes intelligible or less intelligible, depends on the room geometry as we talked about. It depends on the source to listener distance. It depends on the signal level, how loud I am talking or how quiet I am talking. Then you term something called signal to noise ratio. Signal is what I am emitting if I am talking, noise is something which is reflected, re-reflected and the background noise level together, you call signal by noise. When the noise is getting higher than the signal, the intelligibility will drastically come down. When the background is very high or the reflections are too high, the noise level, that is the denominator, is going to go up. So signal to noise ratio will come down, which means either I have to exert myself to be more loud or you will not have required intelligibility. Then it depends of course on the background noise level. A quick example, two things are to be noted here. You take a specific reverberation time, say let us take a reverberation time of 0.4 seconds. Two things are there, normal hearing and hearing impaired people. There are two columns here. This percentage indicates how much percentage people can understand the signal. If I am lecturing, how much percentage of my communication is understood. When the signal to noise ratio is quiet, that is almost the signal is very strong, 92.5% can be understood for a normal hearing capacity person. As the signal to noise ratio reduces, 0 dB means noise is almost equal to the signal, only 47% or less than 50% can be understood. For hearing impaired people, it is furthermore only 25% of what you talk would be understood, close to 25 to 30% only could be understood. It also depends on the reverberation time. Let us take say 12 dB signal to noise ratio, that is signal is strong but still you have little amount of noise. For a normal person hearing, you have around 90% when the reverberation time is very low. When the reverberation time is around 0.4, it reduces to 82-83%, goes all the way down to close to 69% when the reverberation time increases. As this increases further, this listening or understanding ability will eventually drop down. From 89 it came to 83 and further down to 69% here. So it is depending on the reverberation time as well as the signal to noise ratio. When I say 0 reverberation time, there are specific spaces in laboratory called anechoic chambers and echoic chamber. Anechoic chambers, these are chambers where the reverberation time is much close to 0. I will show you few pictures when we talk about acoustic material. The directly opposite thing for this is a reverberant chamber. Reverberant chamber. Here RT is almost low, here RT is really high. The reflections it is made of polished reflective metal surfaces. So, the reverberation time is really high in reverberant chamber. These are typical laboratory settings commonly used for material testing or testing the noise levels from sound sources. I have put few dependencies of reverberation time. For example, RT, as the room volume increases in meter cube here, the reverberation time recommended increases. As your hall is bigger and bigger, the reverberation time for, say, this is for speech and this is for music, the reverberation time, for example, 100 meter cube hall for speech you will require an RT of 0.6, if it is for music you will have 0.9, whereas a 10,000 meter cube hall, a large hall, the dotted line indicates it may not be very much suitable for speech presentation. If you take slightly, say, around 5,000, you are allowed or permitted to go up to an RT of 1 or 1.2 meter per seconds. If it is a music performance, you can go as high as 1.6 or higher. It depends on the room volume. It also depends on the frequency. Ideally, this particular calculation which I told you, the absorption, here is where the absorption coefficient in frequencies come into picture. RT varies from frequency to frequency. So, the allowable reverberation time also varies for speech and for music with different frequencies. You may require a lower RT in certain frequency. For example, the RT permitted may be lower for high frequencies or higher in low frequency. Mid frequency more or less is taken as a center point or the balancing point. One simple example, we had a circular hall where the reverberation times were estimated. I am intending to tell you here that it is also a function of the space or location where you are sitting or standing in a particular room. This is a circular room. What you see in terms of gradation is the reverberation time T30 here. This is at 1000 hertz. It varies somewhere from 1.2 or 1 second. At specific points close to the center, you are finding reverberation time of around 2 or say 1.8 or 2.2 up to 2.2 seconds we found. So, it is also a function of the location for larger halls, for the location in which you are seated. You may not observe spatial variation in small classrooms, but if you are located in a very huge auditorium, from a position here in one end to the center to a further seat behind or this position close to the stage, you will find a reverberation time difference if you are experiencing the sound pressure. Recommended volume per seat for different spaces. If you see rooms for speech, the numbers are lesser, allowable, this is simple thumb rule. If you have per seat how much volume you can give, that is how huge the room can be. And the other side of it, it goes all the way to churches or concert halls where the volume per seat is very high. As I said, it is a factor of the instruments used, the type of performance done there, it determines seat and the volume, how much volume you allow. There are other indicators for acoustical quality. Articulation index is there, you have speech intelligibility index, speech transmission index and clarity. We will look at these things in the following module. Thank you.